Hello, everyone. Welcome to my talk. My name is Meng Zhang. I'm a postdoc fellow with the Department of Electrical and Computer Engineering at Northwestern University. Today, I will be presenting our CISS paper entitled Mechanism Design for Large-Scale Network Utility Maximization. So this is a joint work with my colleague, Dr. Dipanshu Vassal, who is also a postdoc fellow with the same department. So we have witnessing an explosive growth in internet, according to the Cisco's most recent report. The number of global devices is forecasted to be 29 billion by 2023. In terms of the average number of the devices per capita, it is going to be 3.6 by then. That basically means that we are expected to be interacting in a significantly and increasingly large-scale network in the future, right? In order to achieve the network resource utilization, we would like to consider the network utility maximization, which is a general framework for efficient resource allocation, scheduling, and learning in networks. So this spans a wide spectrum of networking applications, such as the user-provided networks, edge, and for computing, network slicing for 5G, and even some decentralized machine learning architecture, such as the federated learning. But however, there are still several unsolved economic challenges here, namely the self-interested agent and asymmetric network information. Also, that is to say, each agent's objective is different from the system designers and requires an incentive to share the network resources with each other and to uh, truthfully follow some algorithms without manipulation. Also, in terms of the network information regarding both utilities and constraints, these are individual agents' private information. In order to overcome this economic challenge, we would like to leverage the economic mechanism design. So this is a promising approach to efficient resource allocation and sharing, considering participants' private information and self-interested behavior. So, and we would like to introduce the well-known class of mechanisms called VCG mechanisms in this case. So basically, they can achieve some desirable economic properties so as to overcome the economic challenges that we just mentioned. But however, in today's talk, we also focus on the technical challenges of implementing these economic challenges. And the first of it is going to be the scalability issue. So basically, these existing mechanisms, including the VCG and its variants, involve solving I+1 optimization problems, where I is the number of agents. So that basically means that in a large-scale network, it is not going to be so scalable, and it can be impracticable due to the too many problems need to be solved for the large-scale problem. The second issue would be the implementation cost. So basically, all existing economic mechanisms require certain modification to existing NUM algorithms. And some of these NUM algorithms have been widely deployed in practice. One of the examples is the transmission cost protocol that we use to access the internet. So it is actually quite practical for us to just implement these economic mechanisms to modify these existing algorithms, right? So in today's talk, the key goal is to design and analyze scalable mechanisms with low implementation cost for large-scale networks. So here's a brief literature review. So basically, the mechanism design is quite a large area, and we only focus on so here we only like to mention the ones for networked system. So basically, related studies these have been designing economic mechanisms that achieve the that to solve the NUM problems at Nash equilibrium. But however, they may sacrifice some desirable properties of the VCG mechanisms. So the second line of studies focused on a faithful implementation of the algorithms. So basically, in this case, the agents are willing to follow certain algorithms that solve the num-like problems. But however, all existing algorithms or mechanisms have overlooked the implementation cost of modifying existing algorithms. In addition, they either overlook the scalability issue or sacrifice some desirable properties of the economic mechanisms. So in order to overcome these challenges, we would like to introduce our system model. So here is our considered model with a networked system with a set of multiple agents. Also, actually, the number of agents is assumed to be quite very large. So it is also the system with a set of multiple network resources denoted by the set n, and each of the agent has a two-dimensional private type information denoted by theta I and zeta I. So theta I represents the willingness to pay or the desire for certain resources, and zeta I represents the network configuration. So basically, UI represents each agent's utility function in this case, which is a function of theta and xi, which is the vector of allocation. And in this case, xi represents the amount of resource n allocated to agent I. And it is assumed to be a strongly convex utility function in xi. In the following, we're going to consider the general resource capacity constraint given by the following format. So basically, the aggregation of agents' influence is kept by a parameter Cn here. So this influence function, which are the functions of agents' network configuration parameter zeta I here. It represents the influence, for example, the resource consumed in the system or the interference generated to the system, exactly. Right? And these are the functions of the allocated resources as well in this case. So the following is our considered problem, which is the network utility maximization problem. It is to maximize the aggregate agent utility, also referred to as the network utility, subject to the constraint that we just introduced, determined by the influence function of all the agents, right? And this problem cannot be directly solved by an optimization algorithm because of the information asymmetric of the theta and zeta, and due to the strategic manipulation of the strategic agent. In order to solve this problem, we would like to design a mechanism, and an ideal mechanism should have the following economic properties. The first of it is going to be efficiency. So basically, again, theoretical equilibrium induced by the mechanism should lead to the optimal solutions to the num problem. And also, dominant strategy incentive compatibility. Each agent truthfully reporting its type is actually a dominant strategy. And also individual rationality, meaning that every agent should not be worse off by participating. Last but not the least, budget balance. The net payment is actually non-negative, which basically means that there's no need for us to inject any money into the system. So we are ready to introduce our first proposed mechanism, the large-scale num mechanism. So it consists of the two parts. The first of it is going to be the message space. So basically, each of the agent should report its type, and it also is a potential misreport, right? In terms of the allocation outcome, we first introduced the notion. Denoted by rho here. So basically, rho theta zeta represents the portion of agent reporting the type theta zeta. And the system designer will solve the following problem. So this is analog to the network utility problem, except that so this problem assumes that all the agents are truthfully reporting, right? So in this case, this Z and P represents the optimal prime-module solution to this problem, where Z theta zeta represents the allocations to the agent reporting type theta zeta in this case. all right? So the following is a description of the allocation and the payment. So each of the agents will receive an allocation, which is equal to the optimal solutions to the problem we just mentioned, associated to the type agent I is reporting. And each agent I needs to pay the payment denoted by HI here. This is characterized by the optimal due solutions to the problem and the influence, and it's also characterized by the result of the outcome of the influence function here. And this is also parameterized by a parameter beta here, which is actually a tunable parameter to make trade-offs between the to achieve different degrees of budget balance. And the first property we can see they can achieve is the scalability, which basically means that because it only needs to solve one optimization problem compared to the case of the BCG, where it actually needs to solve I+1 problem in this case, right? And also, in terms of the properties it achieved, the first property we can characterize is the dominant strategy incentive compatibility. Basically, as the number of agents goes to infinity, we can actually prove that it can actually achieves this property. The reason that basically means that the truthfully reporting is actually a dominant strategy for every agent. And the key idea of proving this proposition is that we can show that the VCG payment converges to the payment that we just described in our large-scale mechanism. All right. And because of that, because our mechanism, we aim to solve the problem assuming all the agents are truthfully reporting. And because all the agents are actually truthfully reporting because it's actually dominant strategies for all the agents, we can also show that they actually achieve the first property, which is the efficiency, as they actually optimally solve the original problems, right? And also because of that, we can, following the above arguments, we can also prove the following properties. And the first of it is going to be the individual rationality. And then we also have the weekly budget balance. And if we tune the parameter to make sure the beta is equal to 1, we can also achieve the strong budget balance in this case. In the following, we are going to analyze the property of the proposed mechanism when I is finite in this case. So basically, we define the following approximation version of the dominant strategy incentive compatibility, which is parameterized by a parameter epsilon in this case. So basically, epsilon in this case characterizes the maximum incentive of misreporting each agent can receive from the mechanism. And based on that, we are ready to introduce one of the key results of this work. So given the finite number of agents, the large-scale mechanism is epsilon dominant strategy incentive compatible, such that the epsilon satisfy this equation. So this basically means that the incentive of misreporting actually converges to 0 at the rate of 1 over I squared in this case, which is quite speedy. All right, we are ready to introduce the fifth property we would like to achieve, which is called superimposability. So in this case, given arbitrary and potentially distributed algorithms, it is possible for us to superimpose a payment rule onto it to constitute a new mechanism which can maintain all the properties and without the need of modifying the original algorithm. So in order to achieve this, we need to define the generalized environment. So basically, A represents the action for each of the agents, such as the allocation, such as the communication and computation actions in an algorithm. And we would like to use the X star, lambda star to denote the allocation and do outcomes of an allocation when the agents are playing A, in this case, right? And here we would like to use this side to represent the suggested action of the of some algorithms, in such a way that when all the agents are playing the suggested action, the outcome of the allocation of the algorithm actually solve the num problems optimally, right? Which is characterized by these two equations. So we are ready to introduce the superimposable version of the previous mechanism. So basically, the action is something we just described. So they characterize the communication and computation action of an algorithm. And the allocation for each of the agents is going to determine by the algorithm xi star, which is a function of every agent's action. And the payment that we'd like to superimpose to each of the agents is having the following format in this case. So basically it is also characterized by the optimal do solutions to the algorithm and by the influence function in this case, right? And we can see that the payment superimposed is actually quite similar to our previous mechanism, but we can prove that under this superimposed payment onto some num algorithms, all the agents obeying the suggested decision is actually a Nash equilibrium. So that basically means that for any arbitrary algorithms that solve the num problems optimally, it is possible for us to impose this simple rule of payments so as to maintain all the properties without the need to like modifying the original algorithm, right? So this is basically the second mechanism we just proposed. So here we would like to make a conclusion. So in this study, we have studied the large-scale mechanism design for networked system. And for the first mechanism, it achieves the economic properties, including the dominant strategy incentive compatibility when the number of agents goes to infinity. And each agent's incentive to misreport its type actually converges to 0 at a rate of 1 over I squared. For the second mechanism, when the number of agents goes to infinity, it maintains all the economic properties, but does not actually require to modify the original algorithm. So this concludes my talk. Thank you very much.